In this video, we're going to start looking at graphs of trigonometric functions. To begin with, we're going to look at the graphs of the sine, cosine and tangent functions, or for short, y is equal to sine x, y is equal to cos x, and y is equal to tan x. We will look at these graphs in both radians and degrees. So let's start off with y is equal to sine x. Often you'll see this as y is equal to sine theta. X is the independent variable, so they're the values that we're putting in, and we will get out y values. Let's just define the sine function. The sine is the opposite over the hypotenuse. I'm going to graph this now from 0 to 360 degrees or 2 pi radians. We will then later consider other values. So what we're going to have then now is 0, just here, so we've got 0. I'm going to have 90 degrees or pi by 2 radians. I'm going to have now 180 degrees or pi radians. I'm going to have 270 degrees or 3 pi by 2 radians. And then finally now, in this particular interval, we're going to have 360 degrees or 2 pi radians. I'm now going to graph y is equal to sine x, and we call this the sine wave. We start at 0, we come up to a maximum value at 90 degrees or pi by 2. We then come down to 0 at 180 degrees. We come down to a minimum value at 270 degrees, and then we come back up now to 0 at 360 degrees. We have a maximum value of 1, and that occurs at 90 degrees. So the sine of 90 degrees is 1, or the sine of pi by 2 is going to give us 1. We have a minimum value at 270 degrees, and that is minus 1. We call this the amplitude. So when we're talking about the amplitude, we're talking about now the height of this graph, or if you like, the y coordinates. So this gives us some rough idea of what we've got. We can see now that we have a 0 value every pi radians or 180 degrees. We say that this particular graph has a period of 360 degrees or 2 pi radians. So as soon as I start the graph again at 360 degrees, it's going to look exactly the same as what we had before, as it would if we went to the left of the y-axis and looked at negative values. So we say the period is 360 degrees. We're now going to look at the symmetry of this particular graph. If you've done some work before with trig graphs, you might have put a line in and you would have said, well, if I have some value just here, let's say that this value is x, we would be asked to find the other place now where we had the same y coordinate. We can say now that the sine, and we'll write it just here, the sine of x will be equal to the sine of 180 minus x. So if I took now some point just here, if I have now the sine of 30 degrees, this gives me one of our known angles. So this is a known value of 1/2. Therefore, I can say the sine of 180 minus 30, which is 150, will also be equal to 1/2. So when we come to solving equations, we can do this by symmetry. We can also say that the sine of x will be equal to the sine of 360 plus x. So if I have a solution here, the sine of 30 is 1/2. The sine of 390 will also be 1/2, as we are now simply going to continue the cycle. So this is what we say. We say now that this is going to be by symmetry. When we talk about the sine curve, we talk about this as an odd function. We can say the f of minus x is equal to minus f of x. So let's consider what that means. This now is simply a case of rotational order symmetry about now the origin. So if I go the other side and I'll start sketching the other side, we're going to come round now to this minimum point right here and then back up to 0. Here we have now minus 90 or minus pi by 2, and we have this minimum of minus 1. So let's just say we had the sine, so let's say, and I'll write it out, we've got the sine now of minus 90. That will be equal now to minus sine of 90, and we call this an odd function. So let's just write this here, odd function. So if we look now at the sine of 30 degrees is 1/2. If I take now minus 30 degrees, I'm going to get minus half. So all we've got now is this rotational order symmetry about the origin. Okay, we're now going to look at the quadrants. This is slightly less intuitive when you have the sine curve. When we come onto the cast diagram in a later video, or the unit circle, this will be slightly more obvious to see. For all angles now, acute angles, those between 0 and 90 degrees, the sine function is positive. So we have positive in the first quadrant. In the second quadrant, that is, these angles from 90 to 180, so obtuse angles, they are also positive. We can see it's yielding a positive y value. Between 180 and 270, sine is negative, and between now 270 and 360, sine is negative. So that gives us some rough idea. If we now look at the relationship with the cosine function, we can say that the sine of x is equal to cos of 90 minus x, and vice versa. And this is a trig identity. All this is telling me now is simply that I can translate this graph to get the sine curve, and the cosine curve from the sine curve. So if I move this now by 90 degrees to the right or left, we end up now with the cosine curve. So let's do a brief recap. Maximum of 1 at 90 degrees, minimum of minus 1 at 270 degrees, 0 every multiple of 180 degrees. This has a period of 2 pi radians or 360, so it will cycle now every 360 degrees. We call this an odd function as the f of minus x is minus f of x. We can see by symmetry now, if we have a value of x, we have the same value when we have the sine of a function 180 degrees minus that value. So the sine of 45 is the same as the sine of 135. Sine of x is going to be sine of 360 plus x, and that comes down to now the periodicity. So that gives us a basic introduction. What I'm now going to do is look at a plot of the curve. So that was a sketch, this is a plot. I've got this now in radians. We can see we've got the 0, 0. We've got now pi by 2 on 90 degrees, 1, pi, 0, 3 pi by 2, minus 1, 2 pi, which is 360, which is 1. So we can see this is going to cycle to 4 pi. It will now cycle to 6 pi. Then if we come now the other side, we can see the rotational order symmetry about the origin. So we've got now minus pi. Then we've got minus 2 pi. So we can see that too is one complete cycle. If I now just zoom out of this, we can see that this curve or wave, the sine wave, continues infinitely to the left and to the right. So we can see this is going to be exactly the same. So that's a brief introduction now to y is equal to sine x, and we can see those key features. So let's just zoom in a little. There we go. Okay, let's now move on to y is equal to cos x. So we're going to look now at y as cos x between 0 and 360 degrees. Let's get a new part up. That's what we want. Right, y is equal to cos x. So cosine x or cos x, and again, y is equal to cos theta. You might have theta, where theta is what we call the independent variable. So we're subbing in values, cos of 30 degrees, cos of 60, and we get now a y output. The cosine of an angle is defined to be the adjacent over the hypotenuse. So all I'm going to do is a quick sketch, and we will look now at the key features. And I'm going to take this initially now from 0 to 2 pi radians or 360 degrees. We start off with a maximum at 0 of 1. So let's go ahead and put these on. This is going to be 90 or pi by 2, 180 or pi, we've got 270 or 3 pi by 2, and then 360 or 2 pi. So 0, we've got now pi by 2, we've got pi, we've got 3 pi by 2, and then we've got 2 pi. Just remember, this is simply a translation of the sine curve. The same shape, the same amplitude, it's just now shifted. So we start now and we come down to 0. So at 90 degrees, the cosine of 90 degrees is 0. We come down to a minimum now at this point right here, and that's going to be at 180 degrees. We come back up like so to 0, and then we come to a maximum at 360 degrees. So as you can see, this is a rough sketch. Doing it on the tablet is quite hard. So our maximum here is going to be 0, 1. We've got now this point right here, which is going to be 90, 0. We've got 180 minus 1. So max 1, min minus 1. 270 is 0. Then we have 360, which is going to give us our maximum of 1 again. We can see that we have the zeros, 90, 270, and so on and so forth. We say now the cosine curve also has a period of 360 degrees or 2 pi radians. So I would cycle this on, and as you can see with the cosine curve, it will look exactly the same. Let's now look at the symmetry of this particular function. If we have cos of x, this is going to be equal to cos of 360 minus x. So if I took this value right here, what I'm going to do is take now 60 degrees. If I look at 60 degrees, I know that the cosine of 60 degrees, or pi by 3, is positive 1/2. I'm now going to look at 60 degrees back from 360, which is just there, and I get exactly the same value. So I can say by symmetry, the cosine of 300 degrees is going to also be equal to 1/2. And clearly we're going to have subsequent solutions for cos x, so cos x will be equal to cos of 360 plus x. And that's fairly intuitive, as this is going to cycle every 360 degrees. So the cos of 60 is 1/2, the cos of 420 will also be equal to 1/2, as we'll see if we continue this. What I'm now going to do is draw to the left of this particular y-axis. What we're now going to see is that we have symmetry. So this is now line symmetry, and this point is going to be minus 90 or minus pi by 2. We say that the cosine function is an even function. So we can say, and let's just write this here. So even function, that is the f of minus x is equal to the f of x. So let's consider this point right here. This point is going to be minus 60. So if I say the cos of minus 60, this will be equal now also to 1/2. We know that the cos of 60, as we've just seen, is also 1/2. So that gives us our symmetry about the y-axis, and we call that an even function. Let's now look at the quadrants. Again, when we look at the cast diagram or unit circle, this is slightly more obvious to see. For all acute angles, cosine is going to be positive from 0 onwards. If we now have the second quadrant, which is now our obtuse angles from 90 to 180, it's negative. 180 to 270 negative, and positive in the fourth quadrant. That is angles between 270 and 360 degrees. Okay, let's just go ahead now and look at the relationship with the sine curve. So if we do that, let's write it here. We can say that cos of x will be equal to the sine of 90 minus x. So with this, we've simply got a translation. So if I just move this graph forward, all I'll do instead of moving it forward is move now the y-axis to this point right here. We can see that if I move the y-axis here, essentially that's moving the graph on, we have the curve of sine x. So that's y is equal to cos x, and we'll just look at graphing. So here is sine x, there is cos x. So we can see if we just scroll out a little, we have now, and I'll take the sine off, we have the maximum 0, 1, pi by 2 or 90 degrees 0, pi or 180 minus 1, 3 pi by 2 or 270 0, 2 pi 1. And this now will go the other way. So we've got our symmetry about this point. And we can see it just cycles. So if we scroll in and out, we can see that will continue now infinitely in both directions. 2 pi, 4 pi, 6 pi, 8 pi. So brief recap. We have now a maximum of 1, a minimum of minus 1, a period of 360 degrees or 2 pi radians. This now is what we call an even function. That is, the f of minus x is equal to the f of x. If we have one solution for cos x at a value here, we're going to have it at the same value that distance back from 360. So the cos of 120, which is going to be just here, let's put that there, cos of 120, give or take, is going to be now the cos of 240. And if I just show that, let's just put that, and we can see that gives us the same value. We can also say now that the cosine is going to be 360 plus x. So we're simply saying that this is cycling now every 2 pi radians. When we look at the quadrants, we have positive, negative, negative, positive, and it's a translation of the sine curve. So that's y is equal to cos x. Let's now look at y is equal to tan x. So y, let's write this here, y is equal to tan x. So let's consider now the definition of tan. Tan is given as the opposite over the adjacent. Later, when we look at trig identities, we'll also see that this is sine x over cos x. I'm going to start with a quick sketch. So I'm going to consider now the graph, and we will have the coordinate axis like so. To the right of the y-axis, that is the positive values, our tan curve is going to look something like so. At 90 degrees, we have what we call an asymptote. This is undefined at 90 degrees, and we'll look at the reason for that shortly. If we now look to the left now of the y-axis, we end up now with the graph coming down here, and we have another asymptote at minus pi by 2 or minus 90 degrees. And that will be just here. We're going to have these asymptotes every odd multiple of pi by 2. So pi by 2, 3 pi by 2, 5 pi by 2, and so on and so forth. So if we look, this is going to be 0, this is going to be pi by 2, or if we like, 90 degrees. Let's just see what this means in terms of this idea of it being undefined. What I'm going to do is just draw now a little right angle triangle. So let's draw the right angle triangle, and I'm just going to put now, let's put a different colour on here. So what we have then is the opposite over the adjacent. So let's call this angle here x, and we'll say that this is the opposite and this is the adjacent. As now this angle increases towards now 90 degrees, such that the length now of the hypotenuse comes up here, the length now of the adjacent is going to get smaller and smaller, such that it becomes 0. So on this, what we have, the length of the hypotenuse comes up here. We can see that O is going to move up here, and we're going to have now division by 0, as the length of the adjacent is going to reduce such that we have 0. We can't divide by 0, therefore it's undefined when we have this angle of 90 degrees. Okay, let's come the other side. What we're going to have then is background like so, and this point now is going to be 180 degrees. We'll come back up like so, and we'll come through, let's do that, and this will give us now our second asymptote. And as we can see now, this is simply going to be now at, we've got the 270, and let's put that on. As you can see, it's not a brilliantly accurate sketch, but it gives us some idea. So this is now 270, and we can say that that is 3 pi by 2. This is going to be 180, or we could say pi radians. To the other side, we'll come round like so. This now has a period of 180 degrees or pi radians. So every pi radian, so let's put this here, period, is going to be pi or 180 degrees. So we can see now that this is going to cycle here, it's going to cycle here, it's going to start again. So unlike cosine and sine, which were 360, this is 180. We have these asymptotes, which means now that the maximum and minimum values are undefined, and they occur at every odd multiple of pi by 2. These zeros occur now at 0, 180, 360. So the zeros occur now every 180 degrees. This now we can say, and we'll write it here, tan of x by symmetry will be equal to the tan of 180 plus x. So if we have now, and I'll write this out, the tan of 45 degrees is one of our known angles. That gives us 1. Therefore the tan of 225 will also be equal to 1. So if I locate that point there, that's going to give me now 45. Let's do that, 45, 1. We're also going to have that point right here, and that's going to be 225. So 225, comma 1. And this will cycle in the same way now, infinitely to the left and to the right. So if we now consider the odd or even functions, we've got now that tan x is going to be an odd function. So tan x is odd, let's write it here, so odd. That means that we have rotation order symmetry about the origin, such that the f of minus x is equal to minus f of x. So like sine, this is odd. So if we have now the tan of minus 45, this will be equal to minus tan of 45. So if we look at this point right here, let's go there. That now is minus 45, and we have minus 1. Tan of 45 is 1, tan of minus 45 is minus 1. If we now look at the quadrants, we have now our values in the first quadrant. First quadrant are the acute angles from 0 to 90 degrees, where all of these trig functions are positive. If we then consider the second quadrant, that now is the obtuse angles from 90 to 180, that is going to be negative. We have them positive in the third quadrant between 180 and 270, and then negative now in the fourth quadrant between 270 and 360. If we look at a plot of this rather than a sketch, let's take that off. This now, and we'll just zoom in on this, we have our picture here. So we're graphing this. Now we don't have the asymptotes on the particular graph, but we'd have one here at pi by 2, 3 pi by 2, and we can see now that this is simply going to be cycling. So you've got pi 0, let's see if we can pick some points on here, and we can see now that that is going to get very big very quickly, and in the same way this is going to get very negative very quickly. So here we are, this is now the rough shape. So if we move along, we can see now that this is going to be cycling every 180 degrees. So brief recap, and then in the next video we're going to move on and look at graph transformations. So with now the tan curve, the maximum and minimum are undefined, as we've essentially got now these asymptotes. A period of 180 degrees or pi radians. We can see that we have these 0 values every 180 degrees. We see now that the tan of x is equal to the tan of 180 plus x. We've seen that it's now an odd function, so the f of minus x is equal to minus f of x. And we've seen that it's positive in the first quadrant, negative in the second, positive in the third, and negative in the fourth. So there we go, that's a brief introduction to the graphs of trigonometric functions, and in the next video we will look at translating them.